All right, advanced placement chemistry. This is day 87. We're coming down to the wire here, and we are going to work through exercises 1 through 10 on the note set that you were given. These are notes from the NMSI, and we're going to use those for our acid-base unit. So we're going to go ahead and let's just start with, I'm not going to read all the notes to you at this time. There will be another video in which I do that and talk about them individually, but we're just going to go for solving the problems on this one. So a Bronsted-Lowry acid base is the one that we're going to use almost exclusively in this unit, and it's typically the one that's used on the advanced placement exam as well. So that definition is that an acid is a substance that gives up or donates a proton. Where does that proton come from? It comes from a hydrogen atom, which has a proton and an electron. And if in some fashion that proton is pulled away, the electron is left behind, you end up with just a proton. And that becomes what's called a hydronium ion. So an acid is a proton or hydronium donor. It gives it away. That's what the word donor means in this context. A base is the other thing. There has to always be a base for every acid in a reaction. That's the thing that accepts that proton. The proton doesn't simply disassociate or leave a particular molecule. It has to be pulled away. And so the base would be the substance that accepts that proton. So here's some examples down here. They made a typo in this, so let's correct this. This should be H2O. So water is a central substance in acid-base reactions. So if you take nitric acid, it's an acid. It gives up that proton. Why? Because the water molecule pulls on it more than the nitrate does. So it will leave the nitrate here and jump over to the water molecule here. That leaves the nitrate as an ion because it lost that positively charged proton. It still kept the electron that hydrogen had attached to it originally, but the proton goes away, and where the proton goes is it goes over to the water molecule. So now the water molecule has 3 hydrogens. It really has 2 hydrogens plus a proton from another hydrogen, but we just call it 3 hydrogens, H3O, and that makes it positively charged because it accepted a positively charged proton. So we talked about conjugate acid bases. So every acid has a conjugate base, every base has a conjugate acid. It's simply the 2 substances that differ by that 1 proton. So right here, this is the acid, and this over here is the conjugate base. That's what CB stands for. For the base, water in this case, since water was the acceptor of that proton, that makes it a Bronsted-Lowry base, and therefore water is the base, and once it accepts that proton, it becomes the conjugate acid. Why is it a conjugate acid? Again, acids give away protons because now the water molecule, which is no longer a water molecule, it's a hydronium ion, can now give away that proton. It can easily be taken away from the H3O in a later reaction. So now this would act like an acid. Again, both H plus and H3O plus, even though they are not exactly the same thing in terms of what their structure is, this is a proton, this is a water molecule with a proton, are both called hydronium. You really don't ever see an H plus just floating around in solution by itself. It's always been pulled away, in this case by a water molecule, immediately. So as soon as it leaves the nitric acid, that hydrogen, that proton, that hydronium jumps over to the water molecule, and so they refer to either of these as a hydronium ion. Okay, next one, NH4. So NH4 is an acid because it has that positively charged, has that extra proton. It's really an ammonia molecule with an extra proton. And when it gets near water, it won't do this 100% of the time. In this reaction, the H jumps away from the NO3 all the time, 100% of the time. That's called a strong acid. In this case, it's a weak acid. Some of these jump away to the water. And what you're left with is The water again gains a proton, it's H3O plus, and then what this becomes, it loses that proton, it becomes a normal electrically neutral ammonia molecule, NH3. So again, you can see the acid conjugate base pair are here. And this water's the base because it accepted the proton, and it turns into hydronium, which is a conjugate acid, because now that hydronium could give away that extra proton to become an acid at some later time. Okay, all right. And finally, we have phosphoric acid, and that can lose, this is what's called a diprotic acid because it has two hydrogens. The first one it gives away very easily. So it's going to come and become this. So there it goes from H2 to just being H. And again, what's just the same as happened in the previous examples, the water picks up that proton to become a conjugate acid. Okay, so there's just a brief overview of what the notes say. Now we're going to go into solving problems directly here. Okay, so let's do exercise 1, and they're asking you to do the same thing we just did on that example. So right here, they give you the entire equation. This should be labeled A. They give you the entire equation. So there is the hydrogen proton that's going to be given away. It's a hydrogen atom right now that's attached to a bromine, but it's going to be given away. So what's going to happen is it's going to turn into this. So this is an acid because it gave away the proton. So that's the acid. And this is the conjugate base. We just label it as they do, CB. So why is that a base now? Because it's got a negative charge. If it sees an H plus somewhere nearby, it could easily attract it back in to go back to that. In theory, it could do that. We'll talk about why that wouldn't actually happen, but in theory, it could do that. So it's a conjugate base. Here you have ammonia, which is a base, and you'll learn some very common bases and acids as we go through this. But ammonia is known to be a weak base. It picks up that proton. Notice it wasn't water that picked it up this time, as in the previous examples. So it picks up that proton to become NH4, an ammonium ion. So this is the base. And the NH4 is the conjugate acid, Ca. Conjugate acid. Okay, now they ask what is the conjugate base of H2S? So they want you to write this reaction, and they're assuming it's in aqueous solution. Generally, we always say that these things are in aqueous solution. So it's going to look like this. H2O plus H2S. Now what you could have written, and there's an alternate way to write this, instead of writing the water explicitly, you write H2SAQ for aqueous, but we're not going to do that here. I'd like to show the water and show how it's involved in the reaction, so I'd like you to do that. So it's going to move over. This is the acid, this is the base, and so this is going to become, the H2O is going to become OH, excuse me, HS. And what happened to that extra proton? It jumped over to the water to become the hydronium, H3O plus. Okay, there you go. So what's the acid was this. I'm just going to write A for acid. The base was the water. It accepted the proton. Once this loses, and I should put a minus sign there because it becomes negatively charged, this becomes a conjugate base. So I can just draw, well, it's getting a little crowded here, but that's the conjugate base, these two. Let me just draw it really small here. And this base and the hydronium is the conjugate acid, because now that this has that extra proton, at a later reaction, it could easily give that away to become an acid. So that's the conjugate acid right there. Okay, and finally, what is the conjugate acid of NO3 minus? There's a minus sign. I'm going to do that one down here just for the sake of space. By the way, you are allowed to do these problems on this sheet directly. But if you'd like to do them on line paper, that's fine, but you can do them in the spaces. So we start with NO3. So if they don't give us another compound for it to react with, you assume it's water. So I'm going to add water here. Like that. Okay. Now it says it's an acid. That means excuse me, it says it's a conjugate acid. That means it has a base that goes with this conjugate acid. Okay, so what's going to happen then is the water is going to contribute a hydrogen proton, a hydronium proton to it to turn that in. So this lost one of the H's and becomes an OH, and the H comes over to this. And since that H is positively charged, there's no more negative sign there because it, as there was there, because it added that positive proton to that, so it's now electrically neutral. What it did though is it did what we've talked about bases do. They accept a proton, so that's what this did. It accepted a proton, so this was the base. And this is the conjugate acid. And then water was the acid in this case. Water can act as both an acid and a base. And so water's conjugate base is OH. So that's a CB. So now that that has a negative charge on it, it can, in a later reaction, accept a proton. That would make it a base. So that is a conjugate base of water. All right, so that's basically how these work. They pass protons. That's what acids and bases are all about, is passing proton. And one last note about this, it produced a hydroxide. That's what bases do. They produce hydroxides. So that's it. We'll go on to the next one. Read the definitions. You should be reading the notes as you go along through these. It assumes in order to solve each of these exercises that you've read the notes. So please do that. Okay, so exercise 2, which is on page 3, says write the simple dissociation ionization reaction omitting water for each of the following. Well, I like to do it with water. Okay, sorry, I want to do it with water, but I'll just talk you through what it looks like without water. Okay, so you're going to put hydrochloric acid into water. That's a strong acid. There are 6 strong acids that you should memorize, and we'll go over those at a later time, but hydrochloric is one of them. And so that totally dissociates, totally breaks apart. So it becomes water. And what happens is, then, is this donates its proton. It totally dissociates. So this chlorine does not stay with any of these hydrogens in a hydrochloric acid when it's in water. This is totally going to move over to that water molecule. So you end up with H3O, the hydronium ion. That's characteristic of an acid. You'll end up with hydronium ions plus the Cl minus. It's all by itself now. It's lost, all of the HCl's have lost their hydrogens to the water molecule, and so this is the base, water. This is the acid, and 100% of those react to form this, which is the conjugate acid. Because now that it has an extra proton, it could donate that proton at a later time to become an acid. And this is the conjugate base, because theoretically, since it has a minus sign, it could find an H plus floating around in solution and have the H plus attached to it. So this is the conjugate base. That will never happen, however. A strong acid totally wants to dissociate from hydrogen. The chlorine says, get out of here. I don't want any of you around. If it says that to a hydrogen here, why would it want to reconnect with another hydrogen over here? It wouldn't. So if you have a strong acid, you're going to have a very weak conjugate base. In fact, almost a non-existent conjugate base, even though technically it is a conjugate base. If you were to have written this without water, the way that they would write that is like this. It would have simply been HCl, aqueous, produces H+. When you write it without water, you usually write the hydronium like that, because otherwise you'd look and if you wrote it H3O, you'd say, where did the O come from? And then over here you have the chlorine. The chlorine's a spectator ion. It's not going to have any effect later on because it won't reattach to any other hydrogens or anything else. So that's what they're referring to when they say write it without water. It would look like that. I like to write it with water because it's an important reactant. It is an acid and it is a base in almost every reaction that, or most reactions that it's involved in. Okay, here's acetic acid. So this is a funny way to write it. It's not a funny way, it's an alternate way, but here's the way you usually see this written. So I'll write